Mute everyone. Yeah, sure, how do you do that? I don't have that. Mute all. Mute. I didn't mute all, but it somehow didn't.
There was a okay.
Yeah, just go ahead. You can do it. Yeah. All right. So I mute everybody. So we can start it over again. So yeah. So this is a joint hosted by the San Francisco AI and AI Camp. The San Francisco AI used to be called San Francisco Big Analytics. We just renamed it not long ago. So today we have two talks. One is from NVIDIA FLARE teams. We're going to introduce our latest APIs and preview some of the ones we are going to release in the next release. But we'll also have a pleasure to have the Rhino Federal Computing Platform company, Adrish, to talk about how they are doing the federated agentic workflows. So without further ado, so I'll invite the first speaker, Holger. Holger is our principal federal learning researcher at NVIDIA, has been working on this for many, many years. So Holger, take away.
Okay, thank you, Chester, and welcome everyone to this first webinar in 2026. Let me share my screen. Yeah, today I'm going to be talking about federated learning made easy, NVIDIA FLARE's simplified API stack. For people who are new to this topic, I want to quickly introduce NVIDIA FLARE and what it is. Basically, at NVIDIA, we believe that federated computing technology is going to be a key technology that we can utilize to avoid certain restrictions that we have for AI model development. Right, one is federation can remove data silos across different countries, different companies, different institutions. This could be hospitals or banks or different government institutions. It has additional benefits like avoiding data copying in some scenarios. The amount of data can be just so massive that it is prohibitively large and makes it basically impossible to share the data in a centralized place. At the same time, federated computing can help with regulatory compliance and help you to get around some regulatory constraints. And it's very complementary with additional privacy-enhancing technology like homomorphic encryption, differential privacy, and confidential computing. So to enable federated learning in the real world, NVIDIA released NVIDIA FLARE as an open source SDK a few years ago now. And from the early days, we have been focusing on enterprise scale and production readiness, right? So we build a mature and secure and scalable framework that's open source under Apache 2 license and can be used in commercial applications. It's focused on privacy and compliance by enabling this additional privacy-enhancing technology that I mentioned already. It's built as a framework and model-agnostic framework, right? So we can use any type of machine learning framework that you might want to use to train your models in a federated scenario. It supports the end-to-end lifecycle management, going from simulation to large-scale production, and supports flexible deployments from on-prem to cloud to hybrid environments. We have examples in the repository from going from different federated learning workflows, starting from federated analytics with tabular data and image data statistics, to different integration examples with different federated learning frameworks, or federated learning with different training frameworks, going from PyTorch to Monai to TensorFlow, Hugging Face, XGBoost, whatever you can think of. Different types of models, large language models, transformers, and so on. Different popular algorithms, starting from the simple federated averaging to swarm learning, cyclic training, split learning, etc. We can support different data partitioning, from horizontal partitioning to vertical. And we are integrated with different MLOps frameworks like weights and biases, MLflow, and TensorBoard. And then, of course, a very important use case is also federated evaluation, where you can do federated model evaluation, or a more comprehensive cross-site evaluation, where each client in your federation also evaluates their model on each other's data. So over the years, FLARE has been applied and enabled federated learning in many industries, starting from healthcare, for medical imaging and oncology, to financial services, mainly for fraud detection, pharmaceutical industries for drug discovery. We have seen use cases in energy system, transportations for autonomous driving, to battery range predictions, and scientific computing across national labs, for example. We've seen both use cases in cross-silo or cross-enterprise federated learning, and we also support the cross-device, where we can support a hierarchical federated learning systems to scale to millions of edge devices, and support training on mobile phones, Android and iOS devices, using PyTorch ExecuTorch. We also have a rich set of research works that have been implemented in FLARE. You can find them under the repository, under research folder, starting with automated machine learning. Now that you have a federated system, you could imagine that each of the clients can have different hyperparameters that might be tuned based on their own local data distributions, like the local learning rate and batch sizes and so on. So we developed a automated federated reinforcement learning system that can tune these hyperparameters in an online fashion to improve the convergence of federated learning. We've done some work on quantifying the potential data leakage between from model updates that are exchanged between the clients and the server, and show that it's actually pretty hard to reconstruct personal identifiable information from those model updates. So there's some work in that direction. We have work on estimating the contribution of each of the clients to the overall model performance. We have personalized federated learning techniques that can combine models in a supermodel kind of fashion to perform better across the board. And recently, we also worked on some more efficient black box fine-tuning models, where you can tune models in a way that requires less computational resources on the edge devices. So next, I'd like to introduce a couple of the real-world use cases we've seen recently of FLARE. One to start with is our in-house use case at NVIDIA, where we had the autonomous driving team building models for traffic sign detection from data sets across China and the US. And this is really motivated by the fact that you cannot copy out the data from China due to regulatory constraints. And then on the also due to the massive size of the data sets. I think the estimate was that it would take several weeks to months to even just copy these data sets over into a centralized place. So copying the models or communicating the models through federated learning is much more efficient. And they were able to show that a global model can learn from both of these data sets to be more reliable in predicting these different parts of the traffic sign. We have another interesting use case at NVIDIA where Holoscan uses NVFLARE to collect data across these Holoscan edge devices that are installed in surgical theaters in the hospital. So Holoscan is a GPU accelerated platform that takes in multiple sensor data and video streams from medical instruments. This is like endoscopic videos and surgical robotics video streams. And FLARE can collect all the user statistics across the different deployments across the hospital. So we get like a centralized view of how the Holoscan devices are being used across a deployment of Holoscans. We also see interesting use cases for clinical trials. Roche has been collaborating with us on using FLARE for getting better real-world evidence for federated open science. They actually gave a presentation at a NVFLARE webinar just last fall. So you can see the recording here as well. Showing a very interesting use case of federated learning and that can inform better clinical decision making. We have Afaris building networks around drug discovery and antibody developability using FLARE as the federation framework. We have the Cancer AI Alliance using federation through NVIDIA FLARE to reshape how cancer research is done by connecting some of the big players in cancer research from Dana-Farber, Fred Hutchinson, and Johns Hopkins, and so on. We have the Eli Lilly TuneLab is making their foundational models for drug discovery available through federated learning technology for their startup ecosystem to fine-tune these models on proprietary data and continuously improve them. And more recently, we've seen the national labs in the Department of Energy using NVFLARE to train large language models across several national security labs to train these models on very high sensitivity data. And in the second half of this webinar today, you will also learn more about our collaborator Rhino Federated Computing and all the exciting work they're doing in this space. If you're interested more about the different use cases of NVIDIA FLARE, you can check out our recordings from the NVIDIA FLARE days we had last September. They are all on the website. We had like many speakers, both from the US and Europe and in the Asia Pacific time zones. So we had like these 2 days where we had different customers and users of NVFLARE presenting, and we're looking forward to seeing more exciting use cases later this year in 2026. But with this, I want to move on to the APIs, which is the main topic of this presentation for today. Um, uh, over the years, we've of course always tried to simplify the developer experience for federated learning practitioners, but also researchers, right? So the challenge is always to move from a centralized deep learning code base to a federated learning code, right? It often requires some complex refactoring and steep learning curves. We try to address this by providing a three-tiered API stack that is designed for a different user persona, right? We provide a client API for practitioners. They can take the existing PyTorch or TensorFlow scripts and adapt them to run in Flare with a few lines of code change. Then we have the JobRecipe API that can enable data scientists to take kind of pre-baked workflows and run them very easily in real-world federated learning deployments. And what I will be introducing today as well is the new what we call a collaboration API, which is targeting for researchers to be able to write a pure Python algorithms, basically hiding the FL framework behind the scenes completely. So let's start with the client API, which is kind of our which has been in NV FLARE for the longest. The idea here is that we want to bring the practitioner into the focus here and enable them to bring their own code and run it in a federated learning scenario with the least amount of changes necessary. So it's also agnostic to the framework, right? So we provide examples of PyTorch and TensorFlow and PyTorch Lightning, but it's not really tied to any of these frameworks. So if you're familiar with like the early versions of NV FLARE, we had like executor and learner classes, which are now abstracted away, and you don't need to care about these anymore. Just using a simple data structure we call FL model to enable the data exchange. And this becomes very straightforward, right? So we can take an existing training code, like here I'm using the PyTorch Cipher 10 tutorial, basically copied one-to-one from their website, just removing a couple of lines of details here to fit it on the slide. You can see the transformations here, data sets and data loaders, the instantiation of the network, the loss function, the optimizer, and then your standard training loop. So in order to make this runnable in FLARE, now we can easily convert this by just importing the client API as FLARE by convention. At some point in my script, I need to initialize FLARE. So the script basically knows that it's running in a FLARE deployment. We typically do this like after initializing all the data loaders in the network one time. So, we don't have to do this several times. And then we introduce this while FLARE is running loop, right? So this makes sure that while now in the federated learning scenario, I'm doing the training several rounds, right? So every round I will receive the current global model state. That model is then loaded into the network. I do my local training as usual. And after the local training has finished, I'll wrap the model updates into this FLARE.FL model data structure to send back to the server. So this while loop is really for efficiency reasons, so I don't have to instantiate the data loaders in the network several times. So from this point of view, you can see that now my training script doesn't have to be restructured into any particular client class or anything like that. So client API makes it very straightforward to convert training code into something that can execute in a federated scenario. If you have a standardized trainer, like a PyTorch Lightning, it becomes even easier. We can just import a NV FLARE client Lightning API, and we patch the trainer, right? So what behind the scene, we use the PyTorch Lightning's capability to add callbacks in the beginning and the end of training, where the callback in the beginning will receive the current global model and in the end send back the update, right? So the code changes become very minimal. And as a practitioner, I can basically take a training pipeline from any of the training frameworks. Let's say Nemo is one example that uses PyTorch Lightning for large language model training at NVIDIA, and we can patch those training scripts directly and run them in NV FLARE in a federated scenario. So since 2.7, which is our latest release, we introduced the JobRecipe as a new API that can focus more on the data scientist point of view. But here we want to get rid of some of the complexity around configuring jobs. It's a code-first methodology where we don't have to do any manual configuration. Everything is Pythonic way of putting together federated learning jobs using this recipe. Another benefit is that we can write a recipe once, but run it anywhere. So the same recipe can run in simulator, proof of concept, and production environment. And this really helps with the speed to deployment, right? We can go easily between local experimentation and then production deployment. And this looks something like this. I can have a Python script that captures some of my input arguments, like number of clients, number of rounds, maybe some of my training arguments, like the batch size, wraps all of it into a recipe. Here, the standard one, of course, is federated averaging recipe. We have others for statistics, for evaluation, and so on. But for Fed average recipe, for example, we have you can give it a name, you give it the minimum number of clients that are needed for the moving to the next round. You define the number of rounds, the initial network. You provide your training script using the client API that we just discussed, and these training arguments. And now the nice thing is that I can define an environment where I want to run this recipe, in this case, the simulation environment, and then just execute it. In the same way, now I can easily switch between different environments. So the same recipe can be executed in the simulation environment for rapid debugging. It can run in our proof of concept environment, which basically runs or spins up a local FLARE deployment with all the multiprocessing, and therefore can enable a realistic testing scenario. And then we can also use our startup kits that allow you to connect with a production environment, right? The startup kits, if you're familiar, include all the certificates that allow you to connect to to a real deployment of the federation in a secure and scalable manner. So yeah, I probably need to speed up on this one a little bit, but the newest API that I want to give you a little preview on today is the Colab API, or Collaborative API. And there, the idea is that we want to focus on the researcher experience. One of the hurdles one of the feedbacks we hear from researchers is that federated learning frameworks in general are restricting them too much, right? They always add some constraint on how they need to write code in order to implement federated learning. And if you look at the publications in federated learning research literature, I would say over 95% is not using any of the existing frameworks. So we really want to change that and enable an easier transition between research and real-world federated learning. So this Colab API introduces a pure Pythonic paradigm, right? We don't have any framework-specific classes or inheritance that we require for you to implement federated learning workflows. And this really gives a lot of academic freedom to the researchers, right? They can purely focus on the logic. The idea is that you can implement swarm learning and split learning, these are more advanced communication patterns without having to worry about underlying messaging or serialization issues. And then within the FLARE deployment, we have a unified wrapper following this job recipe concept called Colab recipe that makes it then again easy to run this in different environments, going from simulation to production. I think the easiest to understand what I'm getting at is just by looking at a simple example, right? So what we have in mind is that we can introduce decorators that tell which functions can be remotely executed by parties participating in the federation. So here on the client, I have a training function. You can notice this is just a very simple function taking in weights, and there's no constraints on the syntax at all, right? All we need to do is we need to add a decorator saying that this function is published and therefore can be executed by a other party. Then we have a main Colab function. So this is going to be our main entry point that runs on the server. In this case, this is the Fed averaging main loop, basically. It takes in initial global weights and then does a number of rounds federated learning, right? At every round, we use the Colab API to get all the clients and then call this train function that has been published remotely, give the weights as the input, and wait for the results to aggregate. And in the end, return the weights. In the main function, everything is wrapped into this Colab API, Colab recipe, and then again executed in the simulation environment. Here with 3 clients, as an example. But looking at this, right, you can see that these published functions can live anywhere, right? It could be on the client, it could be on the server. There's basically no constraints here. So now if I want to think about a more complex workflow, something like split learning, where I have part of the model running on the client and part of the model running on the server. In this case, I'm assuming that one client is the data holder. It takes in it has a forward function, so it takes in a data batch, computes activations, and these activations are being sent to the server, right? So if you look at the main function that runs on the server, we have here our main loop, where the server calls the client's forward function. In this case, there's only one client to get the activation. Then the server has a label, so it computes the loss and the gradients, sends the gradients back, and the client in this case has a second function that has been published called backward to complete the backward pass on the model on the client, right? So it's very straightforward to implement this with pretty much becoming like you would write a pseudocode in a FL research paper. Behind the scene, the core functionality of the Colab API is this remote object invocation, where we provide a logical connection between the server and the clients to be able to remotely invoke these functions. And here I'm saying train, right? But there's no restrictions on how this function should be named or what the syntax is, what the arguments are, or the return values. All the messaging and serialization will be hidden behind the scenes. We will have different flavors of this available, right? You can, by default, have a blocking call, right, to implement asynchronous federated learning. But then we can also have blocking false calls to enable asynchronous execution for efficiency. And you will be able to do like a Colab context to select individual clients. For example, instead of selecting all clients at once to do a parallel remote object invocation, you can also do like individual functions at different parties. So just to summarize these new decorators that we're introducing, right? There's the main entry point for the algorithm, the publish, which is exposing the function that can be remotely called. This could be either on the server and the clients. And then we also have additional init and final decorator functions that can be useful for setup and tear down of resources. So sometimes useful for software engineering. So let me quickly show you a demo so you get an idea how this looks when you actually run this. So here I have a simple federated averaging script, right? I initialize a linear model with a forward pass and my train function here. Again, I'm using this Colab publish. It's a very simple example, so the data is actually just randomly generated. I can initialize the model here, and every time I get the weights, I will load the weights dictionary into my model. I have my optimizer, my loss, my local training loop here, and I return the state dictionary after the local training. On the server side, I basically have a simple averaging function to do the aggregation. And here's my main Colab function that basically starts the job to do the federated averaging. So when we look in here, we define the number of rounds, initial global weights, and then execute for a number of rounds. The main thing is here that Colab clients.train can take in the global weights, receive the results from all the clients, call the simple averaging, update the weights, and then after this is completed, returns the global weights. Again, the framework, the Colab API doesn't restrict you to write any of this code, right? You can define all of these functionality freely. And then we can wrap this into a Colab API recipe and execute in the simulation environment. So let me run this. So now you can see this is behind the scenes. It's setting up the simulation environment. And you could probably notice this runs very quickly. One of the advantages now for simulation is that by using this, we can run everything in memory and therefore get a very efficient way of simulating this new paradigm. Okay, let me go back to the presentation. So with this new Colab API, we really want to give simplicity by design. The core idea is that what you think is what you code, right? You can freely express the communication patterns and workflows you want to implement in your fancy new federated learning algorithm without having to think about network topologies and things like that. With those two simple decorators, you basically can define all kinds of workflows I think we can think of. So it should be pretty straightforward. As I said, there's no messaging logic that is exposed to the developer. So it should be pretty straightforward to implement the research algorithms. And by having this clear and intuitive roles, we don't really need to have any heavy inheritance from controller, executor, base classes, and you can freely develop your code as you see fit. So I quickly want to just summarize the APIs again. We have the client API and JobRecipe to go from 0 to fully operational federated learning and about 10 lines of code change. We have the flexibility by reusing existing assets with the client API. You can easily convert the existing machine learning workflows to federated learning. Scientists can easily experiment with the recipes in both simulation and real world production deployments. And with this new Colab API that we're targeting for the next 2.8 release, we want to enable researchers to freely innovate on new research ideas. And everything will be production ready to run in a mature and secure NVIDIA FLARE runtime environment, which has been used across the board in medical imaging, drug discovery, financial services, and scientific computing. So with that, I want to thank you for your attention. And as always, reach out via email, check out the website, and feel free to engage in discussion on GitHub. Thank you.
Thank you, Holger. I'll open up give a couple of minutes for questions. If anybody has a question, please post your question on the chat. There was originally some questions has been asked and already answered by the post. Let's see. So somebody was asking, let's see. Yeah, I hope I pronounce your name right. Email. You're saying that whether FLARE has the secure aggregation implementing, for example, using homomorphic encryptions, and do you support integrating your own custom secure aggregation protocols? Of course it does. So you can implement the FLARE. FLARE is actually doesn't control what type of implementations. All the implementation you can consider is examples. So so you can change them.
There are many tutorials available on the website.
Yeah, so their question is, Jeff is a question, are there tutorials available? Yes. we have several hundred, probably several hundred examples. I'm trying to delete some of the examples as some of the examples are obsolete. So we recently, still haven't reflected the latest API, but there are recent published a 5-part, 12-chapter tutorials, which have 105. I'll send a URL in just a second. It was 105 notebooks and 80, I forgot, 80 81 videos. So there's a lot of them, and there's also a tutorial website that you can go through them. Question: the resource cost for my nodes has been a problem. What's NVIDIA doing about it? I think this is this is kind of it's not a short answer, because if you have a machine logged in with a GPU 24/7, of course the cost will be there. But how do you scale it? There's a multiple way to scale it. You can have a light, like a client, and then using other resources, like for example, some of the people using HPC and all the others you can farm out the heavy computing there. The other solutions, which is coming out in next release, is our native Kubernetes support, so you can do auto scalings. Goes from there. That will be our coming release. So let's see. Can you share the PowerPoints? Can we share, Holger?
Yeah, of course.
Yeah. So some people asking for URL. We'll post URL just a second. Let me see. What safeguard does FLARE implement to protect the fed learning model from data and the model poisoning? Holger, can you take this one? He's asking. Yeah. Okay.
Yeah, there are different ways of implementing things like more robust aggregation methods. You can basically detect outliers in your model updates from the clients. And yeah, in worst case, you need to reject those if you assume they're from a poisoned distribution.
So there's a question, something about recently I found it impossible to include data splitter components when using Recipe API. This is possible. I could just include data splitter in it. Probably you can ask this, put something on the issue. I'm not sure exactly your problem on the including splitter in the Recipe API. Either create a GitHub issues and we'll respond to that. We'll monitor that.
Yeah, we've done a lot of updates recently, so not sure which data splitter you're referring to.
So the cost, talking about electricity cost, that's too general. Okay, so I think we need to switch. You can continue asking a question, and we can try to answer on the chat. But we should switch to the second speakers. Thank you, Holger, again. So our second speaker is Adrish. Adrish is the VP of Customer Success at Rhino Health, and Adrish is going to talk about the agentic workflows. Adrish?
Yep, I'm here. Let me share my screen. You can see my screen, right?
Yes.
Okay, very good. Yeah, thanks, Holger, for the great presentation. And good morning, good afternoon, or good evening, everybody. My name is Adrish Sanyasi. I lead the customer solutions and delivery organization within Rhino Federated Computing. We're the company that is taking federated learning and federated computing concepts to large enterprises. Some of our initial customers that I think Holger already mentioned, Cancer AI Alliance is running Rhino Federated Computing behind the scene. Also, we are the platform behind Lily TuneLab, and we have many other customers in healthcare, life sciences, and also in financial services, and we're also in other verticals like energy and public sector. So what I'm going to talk about today is you all, if you're attending this session, you already know what agents are, agentic paradigm, etc. One of the things that I want to talk about today is how some of the concept of federated learning and federated computing in general, how this is highly applicable while you were developing and deploying this agent and agentic infrastructure for solving any vertical specific business, complex business problems for your own organization or maybe for your customers. So agenda for today is why federated approach for agentic AI, and then talking about some of the architectural and execution modes that we found is highly relevant. And then we're working on a number of different pilots and production implementation right now with our customers, and I'm going to share some of the learnings as a checklist item that would be a very learning opportunity for us to consider. And that's kind of the presentation today. I'm going to show a little bit of the product as well if the time permits, but you can contact me later for for any detailed presentation. So in terms of the some of the capabilities that any agents or agentic applications, I'm talking about creating a systems of to solve a problem, and these are some of this following characteristics. Like you want to deploy agents in enterprise to solve a problem that might require not only an inferencing a model, but also a lot of other tasks that you might need to. You need to read the data, you need to do some kind of quality checks, or maybe you want to run multiple inferences and reasoning steps, etc. So it requires agents to work safely with your data sets and then adhere to some of the security, identity, and all the access management principles behind the scenes so that it can be run safely in a customer environment. The second thing that we need in order to implement agent is you want to not just implement it in one region of the enterprise or maybe in a single business unit. Maybe you're looking for implementing it across the globe, maybe in different regions of the globe, and also within a different business units. And some cases, they may not be sharing data with each other, similar to what we see in federated learning, or in some cases, just moving data into a single place is just not practical because of the variety of reasons, including cost and also the time it takes to move data into a single place. But you really want a global reach. The third thing is, while you're doing this agent implementation, some customers might worry about their data leakage and all the privacy, especially in a healthcare, life sciences, and financial services types of organization. There's a lot of compliance risk for exposing PHI and PI information. And also on the other side, people who are developing models, they may worry about the leakage of the model weights and other things while the agents are running in a customer environment. The fourth one is orchestration. As you can see, the federated learning by design needs an orchestrator, the server that in the case that Holger mentioned. So this concept of orchestration is very important when you're developing the agents. While you are doing federated learning or you are implementing the inference or running in kind of compute jobs, you want to have a control over what agents are doing while agents are actually running in the different ages. So this pattern is from federated learning is highly applicable for any kind of orchestrated agent implementation. And lastly, in federated learning, while you do that, we always worry about this regulatory compliance, making sure that we support all the security aspects, all the data protection aspects, and also log and audit everything, all the actions that is happening, provide reports, support the audit cycle, etc. So those we do by default in a federated learning environment, and this is highly applicable for any kind of agentic AI implementation. So these are the kind of requirements we see in agentic AI. Now let's talk about a little bit details of how these problems are surfacing, while we're seeing implementing the agents, and also how the federated paradigm can support this solving of these problems. Now, going a little bit detail into the execution model, the agentic AI by design, as I mentioned, is a highly distributed, because you have someone have data in a customer VPCs, and the models are owned by somebody else. It could be a model developer, a third party, and then compute may run in a multi-cloud settings. It could be running in a different clouds, or the major clouds, or maybe running in an HPC environment in an on-prem, or could be other types of new clouds environments. And then all the decisions that the agent making behind the scene must have some kind of guardrails and policies, so that it supports the security of the organization. But also, one other thing, I think there's a question on the cost also, that agents are running, and then there's a runaway cost. So there's a opportunity to introduce some of the concepts of FinOps, etc., as a part of this, and we do that also as a part of our platform in general, and also some of the things like adhering to geographic restrictions of the data, and so on. And then, as I mentioned, the secure execution of autonomous agents is a really one of the major requirements while implementing these kind of agents in any industry in general, and of course in an industry that we work with is highly relevant. One of the major thing that I want to point out here is that there are, in a federated structure by design is two-tier. I have a server, I have a client. And like you can see, while I'm working with a lot of these customers, we also see this kind of two-tier architecture for agents. For example, the tier one agents I think about those are like a local agents that doesn't require a lot of orchestration. Let's say you're getting a new data sets coming in, and you want to index a new document, or you want to get a new set of records that is coming from your systems, and you continuously running an ETL jobs to create some outputs. That doesn't require a lot of orchestration from the servers. That's kind of running it like you can create the Airflow jobs, and they can run in a continuous basis. That's a kind of an example of a kind of agents running behind the scene at the edge, and doing something useful. The second type of agent that follows this, paradigm of federated computing and learning is this agents that requires a trigger from a user or some other program, that has some kind of interface, and that interface saves an intent, like in the form of question answer or in form of request. And then request gets broken into pieces of workflow task and execution model, and that execution model gets sent to different edge environments for further task execution. And that paradigm is what we saw in a federated learning that we could implement using the same type of architecture that we have for federated computing. So these are kind of the how federated computing relates to the problem areas that we want to solve in the agentic AI. So now let's talk about some of the things that we already have in the product, and also evolving the product for agentic implementation. But some of the things that we started doing federated learning, federated analytics, and federated computing in general, and we started implementing this two-tier architecture. So first part of the architecture is the Rhino orchestrator, and that Rhino orchestrator has a REST API, and that can connect to either a existing application that we develop and a web UI that connects to an SDK for the purposes of execution, but it also connects to some kind of custom applications. But behind the scene, what's happening is there are a lot of these administrative activities and model capabilities that's there already, like a permission management, for example, is a big one. Role-based access control. Not everybody has access to run the code, or maybe not everybody can download the model weights, or can see the data, or can see the statistics, etc. So you have a detailed permission management system to help that kind of granular control. The second thing is we provide the logs of all the activities. We have metrics and traces, so that the two aspects of it. One is that for audit purposes, but second thing is you need this kind of thing in order to debug a complex distributed system like this. And also we continuously create health metrics so to understand what tasks are running in what environment and what kind of problems that the job might have while it is running. A lot of jobs are kind of longer run jobs, not like running for a couple of seconds. You could run a training. If you run a complex inference, it's running for a number of hours, sometimes a days. So it's important to have a health metric check every couple of seconds. And then the third part is asset inventory. So we have a catalog, and then the catalog has two kinds of catalog. One is the catalog of the data. You can see across the enterprise, across your Federated network, what kind of data you have shared and what kind of data is shared by the participants in the organization. And in some cases, those can be protected. The identity of the data source could be protected, but you can see the metadata information about those data sets. And then you also have a way to have a model registry, and then we're extending this to create like a tool registry and a registry for the agents and so on. It's a very similar concepts that we provide. And of course, the fourth component is a federated orchestrator. That means you have all the FL server, and also there's a bunch of other types of orchestrator for understanding for converting the intent into task, workflow manager, and also we do federated analytics. And in general, that has also have a little bit of different orchestration mechanism. And next thing is we talked about, I think one of the questions was around scalability and metering. So let's say you are running a training jobs or inference jobs in your different agents sites, but you don't want to pay for GPU 24 hours. So you need a way to, on demand, create an instance and then run those in that instance and then shut down the instance when the run is done, so that you're not really paying for GPU all the time, but paying only for when things are running in that environment. So doing this kind of on-demand scalability is a kind of requirement right now, because of a lot of the customer has a GPU constraint, first of all, and the second thing is running all these things in a GPU is expensive for most customers. And then we're implementing like a metering system, like a FinOps managing the cost, helping the customer managing the cost of running all these things, and also creating some kind of incentive system or tokenization type of token system where you are incentivized to share the data in the federated learning purposes, and you get some credit for inference and so on. So working on this kind of marketplace mechanism that is required in order to make federated learning really useful and business ROI driven for many of our participants. And lastly, we have a concept called attestation. That means it's a part of the confidential compute infrastructure that we're implementing, that every code is checked for validity, and we support all that confidential compute components, CPU and GPU components, as long as it is supported in different clouds. A lot of there's restrictions in supporting confidential compute, but as long as it's supported by the cloud provider, we also support that. But as a part of that, we also provide the software attestation where the piece of code can be verified before it is running on the edge. So these are all capabilities that helps with the security, privacy, and some of the concerns that customer has in implementing federated learning. But now to think about, these are the same concerns the customer has in implementing any kind of third-party agents, and that's why this architecture of orchestration is really applicable for implementing autonomous or semi-autonomous agents. Now let's talk about the Edge client. That is another piece of software that's can be installed in all the different cloud VPCs or on-prem environment where you have the piece of data and you connect it to some kind of data sources. The data sources could be a SQL database, a data warehouse, or could be a cloud storage or network storage like a NFS or SMB, etc. And some of the cases we support the industry-specific data models or data sources like FHIR data APIs or DICOM APIs and so on. And this piece of software is actually where all the local executions are happening, starting from connecting to a data source, running data transformation jobs, running the training and all the pre-processing and post-processing, and then getting the outputs, and then sending the results back to the orchestrator for the purposes of aggregation using the NV FLARE algorithms, or the purposes of showing the metrics in case of federated analytics. So that's the kind of the overall two-tier architecture that helps with the federated computing and federated learning, and this is the architecture that we're also using to implement our some of the early versions of our agents and tools. And this is the two-tier model that I already described. There are two types of agents that we see that we have customers are asking us. One is this kind of orchestrator agents that takes the intent from a chatbot or from some kind of front end or request or another application and converts that to a workflows, and then communicate to Rhino API so that we can run things in the edge nodes, and we can incorporate some of the commercial LLMs here. We connected to OpenAI for a lot of customers, and then also can do Gemini and Anthropic. And in the case of the edge clients, we support, some of the products support a lot of the open source models, like we using, BART and other models, and JMA, etc. But also we can connect it from the edge client to some of the private APIs and the secure version of Anthropic or secure version of Gemini and so on. So there's every cloud providers or the model provider has a HIPAA compliant versions of their API, and we connect to those as well. But using this approach, you can connect to a lot of other types of API, like let's say secret manager or cloud APIs that might be required in order to communicate back and forth between the cloud APIs and also this Rhino Edge client. And this is the generic execution model that we follow, and this is it came from our experience in running federated computing and federated learning, where we'll be receiving a request from an user, and that's the control plane. The orchestrator has an agent, and that is planning the work, translating the intents of the request to some kind of static workflow. That is mostly the work currently we're doing, but also in the future we're going to support a dynamic workflow or the series of executable tasks, and that then a control plane then activates this task, basically a piece of container of the code, some people call it tools, and that sends to all the different clients. It could be one client, could be multiple clients to execute the code, and of course it's all encrypted while in the rest, and also at the transmission. And the decryption of the container, the code happens in the locally, and it runs all the different tasks. And also, depending on the output, it can run multiple scenarios, multiple tasks, and this is where the agentic components comes into picture. Some of the decisions you may want to present to customer or for user. Some of the cases you might want to make a decision yourself and run the iterations, and then ultimately you produce the results. And results could be a model weights, or could be statistics, or could be inference output, or could be some kind of transform data. And then we apply this kind of guardrails. One of the guardrails is called k-anonymity and anonymization. We can apply de-identification of the data, differential privacy, and so on. So apply those filters, and then those Results get sent to the orchestrator or the control plane, and control plane process the results, like updating the weights, or maybe creating some kind of statistical analysis output or visualization, and then that gets presented to an application or APIs or some kind of next steps. So that's the kind of way it works. And these all came from our experience in implementing this two-tier architecture for federated computing, but we see it as a highly applicable for some of the use cases we're seeing in the agentic AI environment. And these are some of the examples that we started seeing and working on right now. One is this real-world evidence agent. This is for biopharma customers who wants to collaborate or work with number of health systems where they have a piece of clinical algorithms that they want to run across multiple sites for the purposes of counting number of patients for certain disease conditions, or running some kind of research studies or real world evidence studies across the board. Using this kind of a simplified approach rather than contacting every institutions and working with the bespoke data models and bespoke architecture. You can just connect to Rhino APIs and a Fire front end that could be a developed or existing front end, and then it could be behind the scene connected to different edge sources for the purposes of running these agents, or purposes of just running some kind of algorithms in these data sets and getting the results back. And then we also not just working with this consortium type of opportunities, but this federated computing is highly applicable for some of the intra-enterprise opportunities. For example, there's a federated RAG implementations where a single enterprise has different product unit and product and business units where they cannot share data with each other. They have a lot of restrictions in the geographical storage of the data sets. But as a researcher, as a pharma scientist, or as a commercial operator, I want to query using Gemini or Anthropic or other models, and do this kind of retrieval augmented generation with my own data. But it's very hard to do today, because of the variations in the infrastructure, where these documents are located, but also applying a lot of the security and privacy principles on these data sets. Like a user, if I don't have access to certain information in the enterprise, the way I can present the information would be different than if I have a direct access to the underlying document. So we take care of a lot of this complexity behind the scene in terms of the aggregation of the results from different RAG systems, but also applying this kind of security and privacy principles so that this could be adhered to some of the existing compliance and security needs in the large enterprise environment. Now, instead of talking about a lot of these vertical use cases, I chose one of the common use case is data transformation or data harmonization, which happens in pretty much all industries, especially applicable for healthcare, life sciences. But we have seen that this actually applies to pretty much any industry, where I have a bunch of data source in the source, but in order to do federated learning or any kind of learning, I need to transform it to a standard data schema, and then that's always a problem. And this is a problem we're solving using a productized approach, where we created a system of data harmonization. That means we take care of a few things here in terms of mapping the schema, mapping the values of different columns, using variety of methodology, including large models, smaller models, embedding models versus keyword search, etc. But also we do take care of a lot of the systematic problems. Like you want to not automate everything. You want to probably present your recommendations from LLM to a human who is a clinical expert or maybe a data engineer expert who can review the output of the mapping, review the data quality, and so on. So we have a kind of system to do that. You also have a system for monitoring the performance, monitoring the data quality, and orchestrating the whole workflow. So we created a system that kind of helps our federated customers to implement this as a part of the federated learning project, or could be part of just any kind of analytics project that they want to do across enterprises, but within the same enterprises, but different product silos. I'm going to use this model just to describe some of the learnings that we have and some of the things that we have started seeing and how can bring in some of the best practices of federated learning as well as best practices of machine learning together for implementing the agentic systems like this. So the first thing is, whenever doing this data, for example, this is data harmonization work, you define a goal. What is the goal of the, and that could be a prompt that user writes, like validate my federated data sets for some parameters. Look at the distributions and tell me what is wrong, if there's something wrong with the data sets. And then map my data sets to a standard model, like, for FHIR or OMOP, and then maybe create some features that I can use. So all of these things could be encapsulated in a nice, prompt. And then behind the scene, right now, these are all static workflows. It is not dynamically do these things, right now, but over the time it will be, dynamic. But currently, we're creating this kind of static workflow where we have this concept of, importing data, checking the quality, mapping the data, then presenting to user, and then creating the ETL code, and then executing the ETL code after some testing. And then after the ETL is done, I can invoke the additional workflow steps, etc. And then lastly, there's a task for, while things are running behind the scene, I want to have a monitoring agent so that I can see whose job is running, where there's a performance problem, where this is, issues, or and to log everything and then take actions and identify issues, etc. So the second step is to identify the steps in each task. So, for example, import data is not a simple task actually. If you have understanding the schema, sometimes you may need to do de-identification. Oftentimes we not just ingest or read data. We kind of create a catalog of the data so that it can be visible to the other participants what this data is without really seeing the data, etc. And then the second step might be the quality, but quality has a lot of the other, different steps in between, including the presenting the recommendation and having a, autonomous agent or also a user kind of helps with the recommendations on what to do with the quality problems. And then the mapping the data, either mapping the schema as well as mapping the values and then presenting to human and running, creating the code, etc. And then executing the ETL is also not just a one step. There's several steps. You want to execute the code in a, first in a, maybe staging environment. Then you want to see the output. You want to implement in a production. So these are the steps that, generally happens in a software engineering, but oftentimes we forgot that these are the things that need to be done in order to actually implement this agent. So, but this is if you break down the task and then deploy in such a way that it could be monitored and tracked and etc. That is valuable. The third is designing the workflow, because now you have this kind of tasks. That these are the tools. Think about those are the tools, or some kind of container that is running a bunch of things. But then you have to stitch things together, because let's say I'm running a data quality agent and I want to have another autonomous agent that is reviewing the code, reviewing the output of the quality, and then giving some recommendations, or maybe a human is looking at it and then working on the next steps. And then once that step is done, then somebody has to approve. Yes, this looks good. Then it goes to the data mapping agent, and data mapping agent does the mapping, present it to human. Then human has to say yes, this is complete and it looks good. and in the future it could be automated, and we understand it. But right now it's not actually completely automated. It's a human in the because not everything is 100% right or recommended by LLM. It's like 80%, 90% right. You still need to have some work. And then ETL codes comes in, and then you do the running the code, and then you do this kind of review and corrective action. So this kind of the workflow orchestration is what we started doing at Federated Learning, but we're now implementing this kind of thing for a lot of the autonomous agents as well. Now, last thing we learn is that all of the best practices in software engineering we have to still do here while you're doing this kind of agent or implementations, like a safe deployment practice, release management process, security guardrails, load testing, latency, throughput management. The challenge is this looks very obvious. But what I've seen is people have different backgrounds. A lot of people come from a machine learning, statistic background. People come from infrastructure, on software engineering. Not everybody knows everything. That's why having a system or methodology in place is going to help us get everybody on the same page, why things are doing, and then have a standard way of doing these things across your different agentic implementation, so that you don't miss these things while you are implementing or deploying an agent in production. Last thing I would say that this is obvious, but logging, monitoring agents, etc., obviously important, and these are part of the architecture that we would implement. And bottom line is, by this time, I think I the message is that for the federated learning infrastructure we implemented, federated computing concept is actually very applicable for agentic system implementation, because by agentic system is by nature is federated, and federated computing domain or learning domain can provide a lot of the learnings, a lot of the best practices that you already do, and take those best practices and implement while you are implementing the agentic AI for solving particle specific problems. And if you want to reach out to us, we have contact@rhinofcp.com. You can just reach out to me by LinkedIn. We're actually growing, and we're looking for people to join us. If you're looking for jobs, and you can go to our website and see our openings, and I'll be happy to attend the conversation. And also, if you want to see that demo in the future, let us know, and we can do a one-to-one demo for you, and also any kind of conversation you want to have. Back to Chester.
Thank you, Adrish, for the great presentations. I think that's great to illustrating how to use the federated compute infrastructure to do federated agentic systems. So I think we're about at time, but we do want to asking audience to give some questions. So if you have questions, please post your on the chat. Or simply unmute yourself. We have don't have I think we're okay if you want to ask directly. Oh, I think it's what is Adrish's contact info. So Adrish, do you just ask him to do the contact at rhinofcp.com?
Yeah. Or you can reach out to me via LinkedIn as well.
Okay.
You just type my name in LinkedIn, and it's I'm the only person in that name.
Okay, so somebody asking how to lower electricity and other infrastructure costs. I don't think that's related to this topic, and so probably can ask in some other forum. Anybody have particular questions for Adrish in terms of federal learning infrastructures, federal learning for agentic workflows? So let's see. Is there any connection between FL and federal agentic AI? Adrish?
Yeah. So the connection is a lot of the workload for federated agentic AI uses the same framework for federated learning, like NVIDIA FLARE for training and fine tuning, and also we use this federated framework for running inference across confidential data and confidential models. So a lot of the best practices and the frameworks are very similar. and we reuse a lot of our previous software implementation and capabilities for deploying the agentic AI.
So any other questions? Let's see.
Yeah, I have a question. This is Shekhar. I have a question regarding the ISO 2700 compliancy or some of the industry standard like a SOC type, a SOC 2 type 2. Are you guys, I mean, by the way, this is the fantastic federated computing engine I come across because I do work in the medical research field. So are there any compliance efforts from your end to get those standards and certifications?
Yeah, those are like a staple. We have to have SOC 2. So we have SOC 2 for last several years. We also have a lot of other certification, like you mentioned, ISO, HIPAA, and GDPR, and so on. So these are minimum thing you need in order to go to any enterprises. So we kind of check the box for pretty much every possible certification. And we can
Right, Tricia,
provide
there's
a
another.
SOC 2 report through our trust center. We have, if you contact rhinofcp.com, with the verification, we'll provide you access to SOC 2 reports.
Tricia, there's a question for you. So are the AI agent installed through Rhino dashboard at edge, client locations?
Yeah, so there are one of the concept we have in Rhino is called code objects. Code object like we have a bunch of Python code, and that has the input schema, output schema, and you can define some metadata there. So think about that's like a piece of executable, and that resides in the Rhino orchestrator as a registry in the artifact registry or the container registry, and then when there is a command gets issued, let's say I'm asking a question or I'm answering some answer, and then that container or piece of code gets sent to the place that you want to run, and you can specify the location, specify the data sets where you want to run to, and then that's the way it gets it gets there. And second thing is you can actually do an workflow engine. For example, we have our own workflow, but you can use Airflow or other stuff to stitch together a lot of this container together so that it can run sequential steps. But all the things, coordination is all central through the orchestrator.
Okay, Adrian, another question for you. Say how these two frameworks, and the FLARE and the Rhino, computing platform integrated seamlessly at large scale.
Yeah. So behind the scene, we use NVIDIA FLARE to run all the federated training jobs. So that we take that, we are very connected in terms of our engineering from NVIDIA side, and we implement each and every version. So right now we're implementing 2.7, for example. So our product is built on NVIDIA FLARE framework. We use all the aggregation, all the communication protocols, all the things you have seen today from Holger. We complement that with some of our own capabilities around security, privacy control, data processing, and federated analytics, and some of the attestation and so on. In order to get to a enterprise environment. But behind the scene, we are built on NVIDIA FLARE.
Cool. So there's a question actually for FLARE team. So I'm using NVIDIA FLARE for my research experiment. So there's only limited base algorithms implemented. Can you implement some of the more baseline, like a client selection, one shot, and other data sets other than CFR 10 for experiments? I can take a step first, and then we'll turn to Holger. So we're hoping the contribution directly from the communities. And so, for example, the client selections, there's somebody already put a PR. We're going through rounds and rounds of approval review process. So we also getting a lot of contributions recently from the different algorithms. So FLARE teams are rather small, so we basically implement something very basic for you to as examples, so you can inspire you to do more. But of course, if there's something are really critical to general, general community, so we probably will tackle. For example, we already have the certain workflows, like for example, besides the basic Fed average and all these things, we have these swarm learnings, and that's kind of a user for actually it is used by the national labs. So there's that kind of thing. Certain things we will do as needed. Holger?
Yeah, I would recommend maybe finding a specific issue as to what exact algorithm you had in mind, because there's a lot of different data sets and research algorithms also implemented in FLARE, that you can explore.
Like for Farmer and Holger has done working with BioNeMos, and those are kind of different data sets. For the other ones, amplified models, and so there's a different data sets. It just depends on the type of a problems, a type of a domain. We may work with a different one. For most basic one, C++10, it was that's easy to illustrate in different type of basic algorithms. So let's see.
Yeah, I just posted the links to examples and research examples in the chat again. So please file issues, and then we can add to the repo.
There's a question maybe for Adrish, and he said, are federated model decisions regulatory compliant, and how it is ensured?
Yeah, I think the regulatory compliance is an activity that we do work with the customers. It's not like our system infrastructure is compliant, but once you, let's say, develop a model, that is additional piece of code. So that also has to go through some compliance, and this is going to be the effort working in individual projects. There is no magical way of making everything compliant from day one. There's some work involved, and we support that kind of work because we have a logging system, auditing system, security monitoring, privacy controls, and so on. So we definitely can support any kind of audit and compliance work.
Great. With that, thank you, Holger. Thank you, Adrish, for the two great talks. If you want to connect with them, they can connect through LinkedIn. And if you connect directly to me, I'm at the Chester Chen. I'm also reachable from LinkedIn, and I'm the product manager and engineering manager for FLARE. So see you next time. Okay, bye-bye.
Thank you. Thanks, everyone. Bye.